Okay, hi guys. So let's start class. Let me just share my screen. So today we're going to be learning about polynomial. We're going to be learning about zeros basically today. So let me get my screen ready. Okay. So we're going to be learning about zeros. So yesterday, as you may remember, we learned about polynomial functions and factoring. Sorry, not factoring. Division, long division. And yesterday at the end of class, you guys said that you kind of understood what division was and why and how it worked. So today we're gonna move on to a new topic, which is zeros. So zeros are pretty cool for a number of reasons. So let's look at what zeros actually are. Okay. So basically, zeros are when you have to so basically, when you graph, let's just draw a graph right now. Not gonna be perfect, it doesn't matter. And now let's just draw a circle, I guess. Okay, there we go, that's a circle. Okay, so basically, there's a circle, right? And it's on the graph. And so the zeros of this circle are actually this place right here. Let me get a different color. They're actually this place right here, where this graph intersects the x-axis, and this other place right here, where the graph also intersects the x-axis again. So yeah, that's what zeros are. They're basically where the graph intersects the x-axis, so you can also call them x-intercepts if you want. And so they can also be called roots, or really anything you want them to. So that's basically it. There's really not much to them. So to solve for them, you have to set y equal to 0, obviously, because on the x-axis y is equal to 0. You have to set y equals to 0, and then you have to solve for x. And if there's two zeros, then it'll magically give you two answers. So yeah, that's basically how it works. Here's an important thing, so let's watch a video on it. So it's called the Descartes rule of signs. So this thing is where basically just by looking at an equation, you can tell like how many real zeros it has. So let's just write an equation here, like y is equal to negative x squared plus 3x or something minus 5. Okay, as you can see, over here it's a negative sign, positive sign, and a negative sign again. So when you look at this negative sign, and then you look at this positive sign, you can see that this thing changed. So obviously, yeah, that the sign changed, and that's one change so far. And then there's another change over here when it turns from a positive into a negative again in this next term. So that's another change. So in total we have 2 changes. So with this we can tell that there's either going to be 2 zeros or 0 zeros. So let's find out why that works, kind of, or something, and how to use it.
talk about Descartes' rule of signs and how to use it to find the zeros of a polynomial. So in the last video, you learned one tool for finding the zeros of a third-degree polynomial.
Can you guys hear?
No.
Okay. I see. Okay, you guys should be able to hear now. Just let me just make it back 10 seconds or something.
Descartes' rule of signs and how to use it to find the zeros of a polynomial. So in the last video, you learned one tool for finding the zeros of a third-degree polynomial called synthetic division tables. This tool works very well, but it can be time-consuming. Additionally, it can be hard to know which values of x we should try first. Luckily, there are several tricks we can use to know which values to use and save ourselves a lot more time. So let's go over this first rule. This first rule is called Descartes' rule of signs. This is telling us how many of the roots of a polynomial are positive and how many are negative. So let's start with the positive roots. For positive roots, if f of x is a polynomial, then the number of sign changes of the coefficients of f of x is equal to the number of positive real zeros, or is less than this by an even number. This is a good definition, but it can be a lot. And what do all these words mean exactly? Well, let's look at an example and see. So, say we had this polynomial, f of x equals 4x to the 5th plus 3x to the 4th minus 6x cubed plus 3x squared minus 2x minus 1. We can count the number of times the coefficients changes signs. First, 4 changes to 3, so there's no change there. 3 changes to negative 6, so there is a sign change there. Then, negative 6 changes to positive 3, so there's a sign change there. And then, positive 3 changes to negative 2, so there's another sign change. Negative 2 goes to negative 1, there's no sign change there. So that means that we either have 3 or 1 positive roots. Now, we can say for sure that we have to have at least one positive root. Okay, so we've gone over positive roots, but what about negative roots? Descartes' rule of signs for negative zeros say that for our polynomial f of x, the number of negative zeros will be equal to the number of sign changes in f of negative x, or will be less than this by an even number. So what's f of negative x? Let's take a look at an example. Say we had this same polynomial that we were given before. If we plug in f of negative x, it will simplify to negative 4x to the 5th plus 3x to the 4th plus 6x.
Okay, so this is actually so you might be wondering why didn't this change, because obviously this sign changed, so all of them must change, right? So no. So the reason why that didn't change is because basically for every x you see in this equation, for every x you see in this equation, you're going to substitute that with a negative x. So over here it says x to the power of 5, and so negative x to the power of 5 is negative x. Sorry, negative x to the power of 5 is negative x. So hence you get a negative number here. But over here, if you do negative x to the power of 4, it becomes positive x instead of negative x, because you're multiplying negative times a negative, which is a positive, and then a positive times a negative, which is a negative, and then a negative times a negative again, and that gives you a positive. So the answer is positive over here. So that's the reason why this doesn't have a minus. Okay, so let's keep on watching the video.
Plus 3x squared plus 2x minus 1. Because even exponents always make negatives positive, we don't change the signs on those ones. So like x to the 4th or x squared. But we do change them when they are raised to an odd exponent. So now let's check the number of sign changes. So from -4 to 3, that is a sign change. 3 to 6, not a sign change. 6 to 3, not a sign change. 3 to 2, not a sign change. 2 to -1 is a sign change. So here we have 2. And due to Descartes' rule of signs, we know that we either have 2 or 0 negative roots in total. Now what are we going to do with these positive and negative real zeros? Well, now that we know how many we have, we can make a chart of all the possibilities of the number of zeros. Remember that because of the fundamental theorem of algebra, we know that the total number of zeros for a fifth-degree polynomial like this one will always be 5. So we can write 5 here. Next, we know that we will have either 3 or 1 positive real zeros. And so we can write that here, and then write down below it here. And we can also write on the right-hand column, on the total number of zeros, we can just write a 5 all the way down because we know we have 5. So then we also know that we have 2 or 0 negative real zeros. So then we can write, in the first column, we'll just say 3, 1, 3, 1. And in the second column, we'll write 2, 0, 2, 0. This represents every combination of the possible positive and negative root combinations. Now all we need to do is solve for the number of imaginary zeros. Remember that every row needs to add to 5. So in the first row we have 3 plus 2, which already equals 5. So there would be 0 imaginary zeros. In the next row we have 1 plus 0, so there have to be 4 imaginary zeros. Then we have 3 positive and 0 negative, so we'd have to have 2 imaginary. Then we have 1 positive and 2 negative. So then we would have 3 imaginary. Then, you'd have 2 imaginary zeros, not 3. If you are confused about this, go ahead and go back to the video or spend some more time with this table.
Okay, so that was the Descartes rule of signs, or yeah. So basically, what that says is the total number. So the number of positive real zeros for a given equation is like the number of sign changes in that equation, and yeah, that's basically it. That's basically what it says. So now let's go back. And so did everybody kind of understand that?
Yeah, I did. I understand all of it.
Midlish, how about you? Did you kind of understand that?
No, I drew like 5 minutes ago.
Oh, okay. So, let's just do a practice, and maybe you'll understand Midlish. If you don't, then I'll just try to explain it. So let's do a self-check or a practice sheet or whatever you want to call it. Let's click on continue and let's get going. So here, let's let it load for a second. So there we go. State the number of positive real zeros, negative real zeros, and complex zeros. So you might be asking yourself, what is a complex zero? A complex zero is like an imaginary zero. So it's like not real on the graph. It's not there. That's what complex zeros are. So yeah. And so they gave us the equation right here. So let's see. Satvik, you can go for this first question. Hello, Satvik. Are you here?
Yeah, I'm here.
Okay, you can go for this question.
Okay. So okay. I think it's wait, wait, wait. Two complex. No. I mean, 0 or 2 complex zeros.
Okay. And
Wait. There's 2 answers.
there's actually 3. So he asked you for the positive real zeros, negative real zeros, and the complex zeros.
Oh, okay. There, 1 negative real zero and 1 positive real zero. Yeah.
Can you tell us how you found out this answer?
Well, because 1 negative zero means like from a positive number to a negative number. So that's 1. And 1 positive zero, real zero means 1 positive number to a negative number.
Okay, I think you misunderstood the concept a little bit. So so every time a sign changes, you have to add 1 to the positive real zeros. So basically, you have 1 plus 1 over here because in this equation it changed 2 times. That means you have 2 or 0 positive real zeros.
Oh, okay. Now I get it.
Okay, so you have 2 or 0, and then you have to substitute negative x into here. So that means you would have negative 5x cubed minus 12x squared still, and you would have plus 4x plus 2. So yeah, that's what you would have. So yeah, that's pretty cool. And so from this you can tell the total number of the number of negative real zeros, and that's 1 root. So that means you're not gonna have this. You're not gonna have 0 or 2 complex zeros. You're actually gonna have something like 0 or 1, or yeah. Okay, yeah. It's gonna be 2 real zeros. Sorry, 2 complex. What? Okay,
Isn't
yeah.
it 0 or 2 positive real zero?
Yeah, it's 2 or 0 positive real zeros, yes. And I think they misspelled the answer here a little bit because there's not supposed to be a real here. It's just complex zeros. 2 complex zeros. So, yeah. It's either going to be. Oh, yeah, you were right about the 0 or 2. Okay, yeah, sorry about that. You were right about the 0 or 2 complex zeros. And then there is 0 or 2 positive real zeros. And you have 1 negative real zero. So yeah, that's the answer.
Basically, I got 2 out of 3 or something.
Yeah.
Okay.
Okay, so let's pick those answers. that one, and that one. Clear the screen, and let's move on to the next question. Okay, so state the number of positive real zeros, negative real zeros, and complex zeros. Okay. So Middleish, how about you do this one?
No.
You still don't understand the concept?
No.
Okay, so basically, so how many sign changes does this equation have? So sign changes are where, like, you see how this is a positive number? It's where it turns into the opposite sign. This is a positive number, and this is another positive number. So there's no sign change happening here. Neither is there one here. But when a positive number turns into a negative number, then there's one sign change. And when there's a negative number turning into a positive number or something like that, then there's one sign change. So how many ever sign changes you have for the given equation, that's how many like positive real zeros. That's how many positive real zeros you're gonna have. Or
Like how many positive numbers there are?
it's like how many positive. So it's where a zero is where the graph intersects the x-axis. So it's basically like the x-intercept. So basically, let's say you have a graph looking something like this. Oops, no, that's not what I was trying to draw. But let's say you have a graph looking something like this. Then this is a zero right here, and this is another zero right here.
Okay.
Yeah, it's where the graph intersects the x-axis, and so there's going to be one positive real zero. See, as you can see right here, this is a positive real zero, because if it was something like this, then there's no zeros in this, so there would be two imaginary zeros. So yeah,
Okay.
that's kind of how it works. So do you do?
It would be so like 0 over 2 positive 0.
What do you mean?
Rishabh, I have a question.
Yeah, Satvik.
So basically, so like on the graph or chart that you drew, so like whatever like a line or something has to touch like the x-axis to get like zeros and stuff, right?
Yeah.
Okay, thank you.
Yeah, okay, so Middleish, I think you had a question also?
No, it wasn't like a question. I was saying the answer.
Yeah? What do you think?
The answer reads 0 or 2 positive real 0
For this
or
equation?
2 complex zeros.
For this equation?
Yes.
For this one, there's only one positive real zero. I already gave you that answer. Because there's only one sign change. So now you have to tell me the negative real zeros and the complex zeros, or the imaginary zeros.
What? I couldn't hear you for a second. Can you repeat that again?
Okay, so I already gave you the positive real zeros. You have to tell me the negative real zeros and the imaginary zeros.
There would be 2 imaginary zeros and 0 or 1 negative real 0.
Okay. So why do you think that? Why do you think that?
I picked 2. No. I picked 2 complex zeros.
Yeah, this is.
Because there's like 2 complex zeros, and the thing is like
So the thing is actually that when you go, there's like two imaginary zeros left.
Yeah. Okay. But how did you figure out the negative zeros?
What?
How did you figure out the negative zeros?
And for the negative zeros, I kind of did the same thing. I mean, for the negative zero, you already gave me how many positive zeros there are, so I just solved the negative one.
Okay. So what you were actually supposed to do is you're supposed to substitute negative x for x. So you're supposed to substitute negative x wherever you see x. So you're supposed to replace this x with a negative x. And once you do that, you have to do negative x to the power of 4, which is just x again. So this just becomes 3x to the power of 4 still. And then you're supposed to do that all the way through. And you get this. And then
Okay, so I think for the negative zeros, it would be 0 or 2 negative real zeros, right?
it's actually only one. He was right, even though he guessed. Middleish, you were right, even though you guessed, because see, there's only one sign change here. See, this goes from a positive to a negative, and then it stays a negative throughout the whole equation. Still, see, there's one sign change here, no sign change, no sign change here either. So yeah, there's only still only one negative real zero, and so you have two complex zeros. So yeah, good job, Middleish. Middleish, do you kind of understand how to do it a little bit now?
Yeah, I understand a little.
Okay, so let's see who else is in the call. Sujit, do you want to do number 3? How about you just try doing it?
I don't get how you're supposed to find the number of positive real, negative real, and complex zeros after you substitute the negative x.
Okay, so the number of positive zeros is like the sign changes, right? So in here normally without like substituting anything, there's like 0 times sign changes here, 1 sign change
So in
here.
this case, there's one.
Well, so basically you have one positive real zero here because there's only one sign change right here. So you have one positive real zero. Okay, so now the reason you plug in negative x is because you want to find the negative zeros. So after you plug in the negative x, you're not going to get any more positive zeros. That's the number of negative zeros. That's the number of negative real zeros. This right here is the number of positive real zeros, and so after that you can find the number of negative real zeros.
How do you
But
find the number of complex zeros?
that's just, so you see like the highest exponent here, it's 3, right?
Yeah.
Yeah, so you just do 3 minus this plus the negative zeros.
Okay, thank you.
Yeah. Okay, so but if you have like anything more than 1, then it can be anything less than that by an even number. So basically, if you have like 2 positive zeros, if you have 2 sign changes, then there can be 2 or 0. 2 or 0 positive real roots to this equation. So then you have to like go through each of these like circumstances, and you have to like do like 0 or something like that, like 0 or 2 complex zeros. So how many ever like circumstances instances of like stuff you have to go through that. Does that kind of make sense?
Yeah, but I still don't get, like, how'd you get 2 or 0?
Oh, I didn't. That was just an example.
Okay.
So Sujit, how many so is positive to a positive sign change? This is a positive number, right?
It's not a sign change.
Yeah, I'm asking Sujit. Yeah. So you just look through all of these terms, and so what is the how many sign changes are there in this equation, Sujit? Sujit, how many sign changes are in this equation? Hi, Sujit, are you here? How many sign changes are there in this equation?
Oh, sorry, there are only 2.
There's actually only one. There's actually only one. As you see right here, a positive to a positive is 0, a positive to a negative is 1, and a negative to a negative is still it still adds 0. So 0 plus 1 plus 0, that's 1. So you have one positive real root, and then you can substitute negative x into here, and you get then you can have then you can find out like the number of negative real zeros. So you have to do negative x to the power of 3, that's negative x to the power of 3 still. And then you have to do 2 times negative x to the power of 2, and that's going to be positive 2x to the power of 2, because a negative number squared is a positive number. It becomes a positive number. So if you have like an even number as an exponent, then like you have to like, and so if you have a negative number as the base and an even number as the exponent, then it becomes a positive number. So basically whenever you have like an even exponent, then the answer is always going to be a positive number. So yeah. And then you have minus 12x, sorry, minus 12 times negative x, that becomes a positive 12x, and you have minus 6. So basically now you have to see how many sign changes there are, and there are obviously 2, because that's 1 over here, 1 still, and now there's a 2. So there's 1 sign change over here, 0 over here, and 1 over here again. Because positive to a negative is sign change, and a negative to a positive is also a sign change. So you have 1 plus 1, which is 2 sign changes in this. So you have either 2 or 0 negative roots. So Sujit, do you know what roots means? Can you explain what roots or zeros actually are? Sujit, can you explain what roots or zeros actually are for functions or polynomial functions? Okay. What do you mean? Okay, so roots. So I'm talking about like functions here. So like something like this, like an equation. What are the zeros of an equation? So the zeros of an equation are where the equation's graph touches the x-axis. So basically they're x-intercepts. So it's where like the graph touches the x-axis. So those are the roots. So basically, that's how you. So that's basically what roots or zeros are. Okay, so so the degree of this function is 3 because the highest exponent in this function is 3, right? So you have 3 as your max real roots. Max real roots. Okay, so 3 is the max real roots. So you have 3, so you have to do 3 minus 1 plus 2, and that's 0. So you can have either 0 or 2 complex roots. So the answer obviously is 0 or 2 complex, 0 or 2 negative, and 1 positive.
Wait, how did you get 0 or 2 complex? So I know that the max is 3, but then shouldn't it be 1 or 3?
No. So basically what you do is you have to like add this positive real roots number, and then you have to add this negative real roots number. So 1 plus 2 is 0. Sorry, 1 plus 2 is 3, and 3 minus 3 is 0. And then you have 1 plus 0, that's 1, and you have to do 3 minus 1, that's 2. So you can have either 0 or 2 complex roots.
Okay, I get it now. Thanks.
Okay, yeah, you're welcome. So I think since there's such a low number of people, I think it's safe to move on. And let's go on to rational zeros. Okay, so rational zeros. Identify all the rational zeros of a polynomial using the rational zero theorem. Also finding zeros of polynomial functions. Okay, so let's find out what the rational zero theorem is. So let's just read all of this, but it's not very descriptive. So if you have a polynomial function f of x with integral coefficients in descending order, where p is a factor of the constant of f of x and q is a factor of the leading coefficient of f of x, then p divided by q is a possible zero of f of x. So yeah, someone had a question? Did somebody have a question? I thought I heard somebody trying to ask a question or something. Okay, that seems like a no. So basically, let's read more of this. So it says, so this is saying, this theorem suggests that if p over q is a rational root, then p is a factor. Okay, no, it's talking about like that specific problem. So let's not read more of this. Okay. So what exactly does this mean? What exactly does this theorem, what exactly is this talking about? So basically, we have this expression right here. I have p over q. And so what do p and q stand for? So let's find out. It says that p is a factor of the constant of f of x, and q is a factor of the leading coefficient of f of x. So let's just make up a polynomial equation, okay? So we have x to the power of 2, sorry, x to the power of 3, and we have plus x to the power of 2 minus 2x plus 3. So it's saying if you have a polynomial function with f of x and blah 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 blah, where p is a constant of f of x, and q is a factor of the leading coefficient of f of x. Okay, one second. Let me just look. Okay, whatever. I was just trying to find something that I can't find it now. So it's saying that p divided by q is a possible zero of f of x. It's a possible zero of f of x. And everybody knows what a zero means, right? It's like where the graph touches the x-axis. Remember? So basically, it's saying that p is the constant of f of x. And so what that means is it's like this number right here. Because this doesn't have a variable attached to it, this is called the constant. So this 3 right here is the constant of this function right here, or this equation right here, and the leading coefficient is like this number right here because it's like the first coefficient and stuff, you know. This right here is a 1 because if there's nothing here, then it means there's automatically a 1 over there. So a factor of 1 is always going to be 1, and this is x squared, and this is negative 2x, and there's positive 3. So yeah. So basically we know p is 3 or 1. So you have 3 on top and you have q as 1. So you have 3 over 1 is equal to 3. And you have 1 over 1, I guess, is equal to 1. So this is a possible zero of this function, and this is also possibly a zero of this function. So it means this can be a zero, but sometimes it's not, and this also can be a zero. So yeah, that's basically what it's saying. And yeah, that's the rational zero theorem. So I guess we can watch the video on it now, which can possibly explain it better than I can.
Let's talk about how to find the rational zeros of a polynomial. Say we have the polynomial 4x cubed minus 3x squared plus 20x minus 141, and we were asked to find the zeros. How would we go about solving this complicated problem? Well, we could use the synthetic division method, but it could take a really long time with a polynomial this large. Let's look at something called the rational zero theorem that can help us to solve this problem. So the rational zero theorem states that if you have a polynomial function like the one we were just looking at, we can write possible rational zeros of the function as p divided by q, where p is a factor of the constant of the function and q is a factor of the leading coefficient of the function. So once we know all the possible rational zeros, we can use synthetic division to solve the problem. What exactly does this mean? That's a lot of words with a lot of different things in it. So let's look at an example. Suppose we're given the polynomial from before, f of x equals 4x cubed minus 3x squared plus 20x minus 141. We need to find the possible rational zeros of the function, so in order to do that, we need to set this function equal to 0. Now, according to the rational zeros theorem, we need to find our possible p and q values. So we can set up the fraction p divided by q. So, for all the possible factors of the constant of our function, that would be p. So, in this case, the factors of our constant, which is negative 141, we will have plus or minus 141, plus or minus 47, plus or minus 3, and plus or minus 1. If you want, you can go ahead and double check that those are all the factors. But now for q, we need to find all the possible factors of the leading coefficient of the function, which is 4. So in this case, the factors of 4 are plus or minus 4, plus or minus 2, and plus or minus 1. We can put these all in a huge fraction where we do, so p over q, which would be plus or minus 141, plus or minus 47, plus or minus 3, plus or minus 1, just all divided by the q values, which would just look like this. It's just like a big fraction. And then plus or minus 2 and plus or minus 1. By doing this, we can find all of the possible combinations. So let's start out with a few. There's quite a few of them, so we're just going to do a few and leave the rest for you to figure out. But we will get plus or minus 141 over plus or minus 4, plus or minus 141 over plus or minus 2, plus or minus 141 over plus or minus 1, plus or minus 47 over plus or minus 4, and so on. So these are all the possible rational zeros of our function. We can use synthetic division in these possible values to find the actual zeros of the function. So go ahead and on your own set up your synthetic division table and find the roots of the function. And for this function, we will have 24 possible roots.
Okay, hold on. I'm muted. Just turn yourself.
Yeah, doing it.
Okay, so does everybody kind of understand what the rational zero theorem is?
Yes.
Okay, so let's do some practice problems on it.
Don't we have a break?
Yeah, isn't it break time?
Yeah, sure. Why not?
Okay, so we come back at 9 or 10?
Yeah.
Okay.
Wait, when does this end?
What?
When does this end?
It ends at 9.
Okay.
Okay, I don't care. Okay, guys. So let's get going. Again. So, is everybody here?
Yep.
Okay, seems like everybody's back.
Yep, I'm here.
Okay. Okay. Good. Everybody's here. Identify all zeros for the function. This. Okay. I think it also wants us to like find the imaginary zeros. This is what imaginary zeros look like. This answer right here.
I is square root of -1.
Yeah. I is yeah, you're right. Yeah. I is the square root of -1. So it's called an imaginary number because a square root of a negative number can't exist. Hence, it's called an imaginary number. And so I is like kind of like the basis of all imaginary numbers. And I'm pretty sure it's like almost the only imaginary number. Kind of. At least it's the only imaginary number that I know of. And so this is called a complex number because it's like being added to like a real number. And yeah. So that's why it's called a complex number. It's because it's like an imaginary number being multiplied and added to like real numbers, if you know what I mean. So yeah. So it says identify all zeros for the function. So it's asking us to find the imaginary zeros, which, to be honest, I don't know how to find the imaginary zeros. So let's just skip those and let's find the zeros for this function right here. So does anybody, if you want to do this one, then raise your hand in the participants list. Okay, Rohan, you can do this one.
Okay, so first we have to find p, which is going to be the factors of the constant, which is 21. So we get that p is plus or minus 21, plus or minus 7, plus or minus 3, and plus or minus 1. And now we have to find the q, which is going to be the factors of the x cubed, and the factor of the x cubed is just 1, so it can just be plus or minus 1. So now we can just try these. So for example, we have to do p over q. So plus or minus 21 over plus or minus 1, plus or minus 7 over plus or minus 1, plus or minus 3 and plus or minus 1, and 1 over 1. And I'm not exactly sure what to do after this.
So basically, after this, all you have to do is like plug in these values into the equation, and if they work, then they work, and then it's correct. If
Okay.
not, then it's wrong. It's
Okay,
not a zero.
so I just tested it, and 1 does not work, and -3 does work. So it cannot be the second one and the last one. So I'm pretty sure it has to be the third one, because I plugged in 7 and it does not work. So it's the third one, -3.
Okay, good job. So what did you get when you plugged in 1?
When I plugged in 1, I get...
You got what? I couldn't hear you. I think you got cut off or something. Hello?
Sorry about that.
Yeah? Yeah, I can hear you.
Can you hear me?
Yeah, I can hear you.
Okay, sorry about that. Someone else was calling. So when I plugged in 1, I got 1 minus 1, minus 5 plus 21. So 1 minus 1 is 0, minus 5 is negative 5, plus 21 is 16. So 16 is not equal to 0. And then when I plugged in negative 3, I got 0. And when I plugged in 7, I got a huge number. It's more than 100. So I knew it could not be 7, and it could not be 1. So the only one it could be is negative 3.
Okay, yeah, good job. So yeah, that's basically how you do it. Yeah, that's how you use this formula. And yeah, it's mainly used for like getting the possible values of the zeros. And now after you like get the possible values, all you have to do is plug it into the actual equation thing. And if it equals 0, if the answer you get is 0 when you plug it in here, then then it works. Then it means
I have
that
a question.
yeah.
Instead of doing the P and the Q things, why can't we just plug it in from the start?
What do you mean? Do you mean you just want to plug in like every single number, like 1, 2, 3, 4, and so on and so on?
No, like from the option choices. Like, why can't we just like plug those in
You
instead
can.
of doing the P and Q?
You can.
Okay.
But if you didn't have like the multiple choice here, if you just had like a blank, then you can have the option of getting multiple choice by using this theorem. By using this theorem.
Okay.
So yeah. If there was no other easier way to do it, then you would use this. So yeah, Satvik, how about you do this one right here? Find all the rational zeros for the function.
Okay. I think it would be -2.
Yeah.
2 also works.
Yeah.
I mean, yeah. I didn't see the 2, so I only saw the -2, so I picked that. My official answer is 2.
You can have multiple answers. As many answers as you want. It doesn't matter. So that sorry.
My answer is 2.
That's it. There's no other ones. Are you sure there's no other ones? Okay, let's find out. So basically you have -2 squared, 2 cubed. That's 8 minus 4 and plus 28. So that's 8 minus 4. That's 4.
Risha, why are you talking? Because, like, you're on mute.
Oh, okay, sorry. So I was saying to Satvik, so are those your only two answers? Because you can have more than two answers. You can have how many answers you want.
I'm good with 2 and -2, yeah.
That's it? That's all you think there is?
Okay, let me do something. I think it's also 4 and -4 and 8 and -8. Oh, okay.
Okay. Okay, so let's find out. So 8 minus 4 minus 28. Yeah, it does not look like an 8. Plus 24. Okay, so that's 4 minus 4, that's 0. So yeah, this obviously works. And I'm pretty sure negative... Oh, the 28, that's negative 14 times 2. See, negative... Yeah. Okay, so you said -4 also works. So let's try that. So negative 4 cubed, that's 64. 64.
I'm pretty sure all of these work.
Are you sure?
Pretty sure all of these work.
Okay, let's find out. So 64 minus 16 minus 56 plus 24. Okay, so after we do this, we should get something close to like, you have 8 from this, and then you have to do minus 16. So 8 minus 16 is negative 8.
I got a question.
Yeah?
Where do you get the 16 and the 56 in the
Okay, so I got the 16 from doing x squared. I plugged in 4 as x, so I do 4 squared, that's 16. So I have minus 16 right here, and I have negative 56 because 14 times 4 is negative 56. Negative 14 times 4 is negative 56. And I have 24 from this 24 right here, which is right here. And x cubed is 64. So yeah, I don't think 4 works. So yeah, this is 72. Yeah, 4 definitely doesn't work. Rohan, did 4 work for you?
Yeah, 4 works.
Are you sure? What did you get? And
I'm sure. Because so you can just actually no, 4 did not work for me. It was 16. It's not 0.
yeah, that's what I thought. So yeah, 4 doesn't work. 4 doesn't work. And now let's try 8. So 8 cubed, I really don't want to do 8 cubed. 8 cubed is 512. 512 minus 64 minus 14 times 8. Oops. Okay, let's do 14
I have
times
a question, but it's not related. I have a question, but it's not related to math.
Yeah, what is the question?
What browser are you using?
It's called Opera GX. Opera.
Yeah,
Yeah, it does look cool. It's not much different from Chrome, if you ask me. I just thought it would be cool, so I downloaded it. I wanted to try it out. So now I'm using it because like my laptop has a virus where I can't let it. Like whenever I search online, like it takes me to like some other website and like records like my search and searches and stuff. So yeah, that's why I'm using Opera, because it doesn't happen in Opera, but it did happen in Chrome. So yeah, that's the reason why I'm keeping using it. So let's do this. So 14 times 8, that's negative 12. And so we write negative 12 over here. Sorry, negative 112 plus 24. And I'm pretty sure 8 doesn't work either, because this is not going to be like equal
Wait,
to
but
that.
like, I just have a quick question. So like, when we do the p over x, so basically all the factors of 24 should work, right?
All the factors of 24. Yeah.
Shouldn't it work?
No. See, those are possible roots. We don't know if they work or not. That just narrows down our search, like
Oh, okay.
scope, I guess. So basically, that just gives us like a multiple choice kind of thing, you know. So 8 doesn't work. Let's try 12. So I really don't want to do that, and I'm pretty sure it doesn't even work. So let's try 3 now. So 3 cubed, that's 9. 3 squared minus, so that's negative. So negative 3 squared is, and by negative 3 squared I mean like negative times 3 squared. So that's 3 squared is 9, so that's negative 9. 9 minus 9 is 0. And you have minus 14 times 3. 14, 14, oh my gosh. 14 times 3, it's 42. 42 plus 24, negative 42 plus 24 is not equal to 0. So yeah, 3 doesn't work either. So I'm pretty sure the only stuff that works is 2. And I don't know if negative 2 works, so let's try negative 2. So negative 2 cubed, that's negative 8. So that's
Negative 2 does not work. It does not work.
Okay, so yeah, the only thing I'm pretty sure that works is 2. So yeah, that's basically how you use this stuff. It's pretty easy to understand, I guess. Also, it should, it should be easy to understand, at least. So, let's leave this and let's learn some more cool stuff. Self-check rational zeros. Let's get out of here. And, let's do some more stuff. It's loading really bad because like I have like a live stream running and I'm sharing my screen on Zoom. So it's using up like a lot of my resources, computer resources, so yeah, that's pretty bad. Okay, so graphing polynomials. So graphing polynomials is pretty cool. You can like graph things. So graphing polynomials.
We did this yesterday.
No, we didn't. We did like polynomial factors and dividing and stuff like that, I think. We did not do this yesterday, I'm pretty sure. But let me check anyways. It's loading. Just a second, guys. Okay, so now let me scroll up. See, we did 2.1 and 2.2 yesterday. Polynomial functions and polynomial factors. The 2.2 is like division, polynomial division, long division, you know.
Yeah, okay.
Yeah.
Okay.
Let's go back into doing this. So graphing polynomials. So graphing is like not really that hard. So all you have to do in graphing is like if you know like the basic form of an equation, you know what it should look like, and then it's like easier to graph stuff. But even if you don't know like the normal form of like an equation or anything about the type of equation, you can still graph it just by like plugging in random points for x and y, and like seeing what you get. You can just plug in random. You can just plug in random numbers for x, and see what the y value you get, and so and like whatever you plugged in, that's the x coordinate, and the answer that you got is the y coordinate. So basically, whatever you plugged in goes right here, and the answer that you got goes right here. So yeah, that's how you like graph stuff that you don't know, and that's how you graph stuff in general. So yeah. Here we can graph to find the real zeros of the function. Okay, so this is a cubic function or an odd function. I'm pretty sure this is a cubic function. As you can see, it says x cubed right here, so that means this is a cubic function. So yeah, we can observe that the x-intercept is only 30, so there's only one real zero. This suggests that there are two imaginary zeros. Notice this equation would have had many possible real zeros. This means it could have taken a long time to solve algebraically. Graphing is another method we can use to approximate real zeros of polynomial functions. Notice we can only approximate the real zeros if the roots are rational. The easiest way to graph polynomial functions is on a graphing calculator, or otherwise it can take a very long and tedious process. Let's review how to graph blah 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 on a TI-82 plus graphing calculator. So as this person said, graphing is like mostly useless unless you have a graphing calculator. I mean, it can be useful to graph by hand sometimes, but most of the time it's like pretty useless. It's just takes forever, and yeah, it's not that useful. You won't get much from it. Not that you
Do you
nothing.
have a graphic calculator?
Yeah, I actually do have a graphing calculator.
What's it called?
It's the TI-84 CE. I'm pretty sure it's the color edition. Yeah, it's like the new ones, like with the colors and stuff. Yeah, yeah, it is pretty nice. Very useful. You can install a bunch of stuff on it if you wanted to. I don't have anything on there though, because I don't have time for such gimmicks.
Wait, can you repeat the spelling?
What sign?
Can you repeat the spelling of the thing you just said?
Oh, it's called the TI-84 graphing calculator. Uh, and
Which edition do you have? Is it called Plus C?
I'm pretty sure it's the plus C. I don't know. I really don't know. Okay, all I know is I have the TI-84 graphing calculator that has color on it. It's like the color edition where it's like the screen is brighter and like it's not like super bulky. It's like a thinner model and stuff. It's like the newer one. Okay, I really don't know much about calculators, so yeah, that's all I can tell you. Um, right now you won't need one unless you're going to like 7th grade or 8th grade. I only bought mine like last year.
What grade are you in?
I'm in 9th. So yeah, let's keep doing more stuff here. Okay, so solving polynomials by graphing, finding zeros of a function, we don't need that. Inverses of functions, so this is a good topic. So inverses of functions, so that looks something like this. See, it's f to the power of -1, and then there's like parentheses x. This is how inverses of functions look like. That's like the symbol, I guess, for inverse functions. So inverse functions are pretty cool. I don't know what you use them for, but I just like them because like the process to solve them is super cool and it's not hard to do. I don't know what you would use them for, like in real life or anything like that, but like